Next big topic in innate immunity is the complement system, which can be overwhelming for some, but I'm going to try to make it really simple for you. I will go through the pathways, but to be perfectly honest, the details of each one are not that important for the boards, or life for that matter, and I really want you to focus on the high-yield take-home points. I'll start off with a general overview, go through each pathway, and then I'll finish by summarizing what you really should know and what to focus on when you're studying. But if it's going to get you bogged down, you're better off skipping it. It probably won't be worth too many points on your exam. So here we go. In general, the end goal of the three complement pathways and what they're all trying to accomplish is to get to the MAC, the membrane attack complex. The MAC is a complex of complement proteins that creates a hole in the cell wall of a pathogen, especially gram-negative bacteria, and ultimately causes cell lysis, very similar to perforin. To get to the MAC, you need two steps, so let's work backward a bit. Complement proteins are made in the liver in their inactive form. One of these is called C5. You need the activated component of C5 called C5b to make the MAC. In order to convert C5 to C5b, you need an enzyme called a C5 convertase. The liver also makes another complement protein called C3. The activated component of this protein, C3b, is necessary to make the C5 convertase. And lastly, you need a C3 convertase to turn C3 into C3b. So from the beginning, the liver makes C3. A C3 convertase turns it into C3b. C3b is used to make the C5 convertase, which can turn C5 into C5b, which is then used to make the MAC. The only thing left unresolved is where does the C3 convertase come from? And the answer is that all three complement pathways lead to the production of a C3 convertase in one way or another. The alternative pathway is the easiest one to understand, so we'll start here. C3 is the most abundant complement protein and is continually being broken down into its component fragments. This happens spontaneously when it binds amino and hydroxyl groups on cell surfaces, but these molecules are much more commonly found on pathogen surfaces, for example in LPS, viral envelopes, and the fungal cell wall. Binding these groups stabilizes C3b, and if it doesn't bind, it's destroyed in seconds. Despite this spontaneous conversion, you still need a C3 convertase to get the mass production of C3b necessary for a significant response. So how do you get to the C3 convertase? Once C3b is stabilized, a protein called protein B comes in and is cleaved by protein D to its active form BB. C3b and BB join to form C3b-BB, which is the C3 convertase of the alternative pathway. This leads to a positive feedback loop and snowball effect as more C3 converted to C3b leads to more convertases, etc. The other two pathways are the classical and mannose-binding lectin pathways, which I like to group together because they're really the same. They just start a little differently. Both involve something binding the pathogen which allows activation of the C1 complex. In the case of the classical pathway, the thing that binds the pathogen is antibody, mainly IgM, but also IgG. The classical pathway is the only pathway to involve the adaptive system. Here are some repeating antigens which can be recognized and bound to by IgM. IgM is a pentamer, meaning it's basically like 5 antibodies grouped together at the Fc region. This makes it easy to bind a bunch of antigen. The C1 complex is made up of C1q, which can come in and attach to the antigen-antibody complex at the Fc region, and also part of the complex is an R and S component, and a protein called C1 esterase inhibitor, labeled here as I. Again, the whole complex is collectively termed C1. When C1 binds IgM, or multiple IgGs, the Fc receptors are brought close together. Again, IgM is naturally a better fit than IgG for this mechanism because the Fc regions in the pentamer are already close to one another and C1 can bind them all easily. When this happens, C1 inhibitor falls off, and R and S become active and form a convertase. So we've been introduced so far to complement proteins C1, 3, and 5. You're probably wondering what happened to 2 and 4. Well, I'm glad you asked. Here's our liver again, which produces C4 and C2. Both are cleaved to their active products by the activated C1 complex to C4b and C2b. These add together to make C4b2b, which is another C3 convertase. The mannose-binding lectin pathway is exactly the same, except like the alternative pathway, it does not involve antibody and so does not rely on the adaptive system. Lectins are acute phase reactants made by the liver which bind carbohydrates, here's our lectin, and in the case of complement activation, lectins can bind mannose, which can only be found on the cell surfaces of bacteria and fungi, but not on human cells. In this pathway, instead of attaching to antibody, the C1 complex can attach to these lectins, leading to activation. Now, once we have our C3 convertases from any of these pathways, the N is the same and is therefore called the common terminal pathway. Remember, from the alternative pathway we get the C3 convertase C3b-BB, and from the classical pathway we get C4b-2b. From here, we said that to get to the C5 convertase, all you need to do is add a little more C3b. This results in different C5 convertases depending on the pathway, but they do the same thing, converting C5 into its split products C5a and C5b. C5b then can join C6 through C8, and C9 is added to make the channel and form the MAC, which can be used to destroy bacteria. C5 through C9 are called the terminal complement proteins. The last thing to mention here is that in the process of forming active complement proteins, smaller inactive subunits are given off. So just like C5 gives rise to C5a, C3 and C4 also give off C3a and C4a when they're cleaved to their active products. And remember, these smaller subunits are the anaphylatoxins we referenced earlier. They're usually degraded, but can sometimes act to trigger mast cell degranulation, mediating a hypersensitivity response. Okay, so we just covered a lot. Now let's quickly run through all of this in the text, hitting the main points again. So after all that, here are the three pathways compared on one slide. In the alternative pathway, also called the antibody-independent pathway because it does not involve antibody, C3 is cleaved to C3b and C3a spontaneously when attached to microbial surfaces. Add in some protein B and you get the C3 convertase, which makes more C3b. In the classical pathway, which is antibody-dependent, antibody binds antigen, which leads to C1 complex activation. In the MBL pathway, it's lectins made in the liver that attach. What do they attach to? Carbohydrates, and specifically mannose, and this pathway ultimately gives you the same result. Activated C1 cleaves both C4 and 2 to give you another C3 convertase. The end result for all three cascades is the common terminal pathway. Like we saw in our diagram, this involves mixing in a little more C3b to make the C5 convertase, and we end up with the conversion of C5 to C5b. C5b adds to the rest of the terminal proteins C6 through C9, and the MAC is in business doing its thing. If you got all that, great. If not, here's a summary of some of the high-yield complement quick hitters to focus on, plus a couple of things we haven't touched on yet. First off, you should know that complement proteins are made in the liver. There are three pathways, all three of which produce a C3 convertase, which converts C3 to C3b. The biggest difference between the classical pathway and the alternative pathway is that the classical pathway requires antibody, and the alternative pathway does not. The mannose-binding lectin pathway is really the same as the classical, but just starts differently. It does not require antibody, but it's still more targeted than the alternative pathway because there's at least some recognition of foreign molecules. And it's important to know that the terminal complement proteins C5 through C9 make up the MAC. This is something we haven't brought up here yet, but we did touch on this in our intro lecture. C3 is probably the most important complement protein, not only because it starts the whole process, but because it gives rise to C3b, which is kind of like the antibody of the innate system. Complement actually got their name because they complement adaptive immunity. C3b is a major opsonin in the immune system, as is IgG antibody. Opsonins coat bacteria, allowing better recognition and binding by phagocytes. Because of this, complement are really good at fighting encapsulated bacteria, which are resistant to phagocytosis, and this is important. The anaphylatoxins C3a, 4a, and 5a are byproducts of the complement system, but they like to test these, so you should know them. And you already know from before that C5a is an important chemotactic factor for neutrophils. Lastly, there are a couple of regulatory proteins to know about. These inhibit the complement system so it cannot go crazy and just destroy us. Decay accelerating factor works by disallowing C3b to bind, and there's another similar molecule called membrane inhibitor of reactive lysis, or MERL, which works by directly inhibiting the MAC. Both sit on surfaces of human cells protecting them. The clinical relevance of this is that there's a disease called paroxysmal nocturnal hemoglobinuria, in which there's a genetic defect that prevents these complement inhibitors from anchoring to red blood cell membranes. Without this protection, there ends up being hemolysis by way of complement. C1 esterase inhibitor, which we have already seen, also helps keep complement in check because it inhibits activation of the classical pathway. One last important point about complement in general is that when the cascade is activated, complement levels in the blood will be low, not high. This is somewhat counterintuitive, but this is because complement is being consumed to form their split products and depositing in tissues. So why do they want you to know all this? Well, like everything else, it's to help you understand what will happen when things go wrong in certain disorders. So what would happen to us if we did not have complement? Early deficiencies, and by this we mean C1 through C4, for example, someone can have an inherited C3 deficiency, will result in a pretty nonspecific spectrum of disease, so they're not terribly high yield. People with these deficiencies get recurrent sinus and respiratory tract infections by encapsulated bacteria presenting in infancy. These bacteria can evade the immune system more easily because their capsule acts as an antiphagocytic virulence factor, and under normal circumstances, C3b would opsonize these bugs to help fight them. These patients require close follow-up because they are also at risk to develop autoimmune diseases such as lupus, especially if they have a C1 or C4 deficiency. Complement proteins of the classical pathway can bind antibody and normally bind antigen-antibody complexes to help macrophages clear them. When not cleared, these complexes can deposit in tissues and cause lupus nephritis and other type 3 hypersensitivities. This is one possible mechanism. We're going to see autoimmunity as a feature of several immunodeficiencies, which is kind of counterintuitive, but overall this is low yield because it's not really well understood. The more high-yield complement deficiency is deficiency in any of the terminal complement proteins, which leads to an inability to form the membrane attack complex. This causes problems with Neisseria and Neisseria only, so it's not as bad as early deficiency. There's still C3b, so most encapsulated bacteria can be opsonized. It's unclear why Neisseria specifically is problematic. So be on the lookout for meningitis, which in a passage will be a college student with a headache, neck stiffness, photophobia, and a petechial rash. Or another way they might test this is having it present as repeated gonococcal infections in someone who is not a sex worker. Someone can also have a complement inhibitor deficiency. The enzyme C1 esterase is responsible for the proteolytic cleavage of C1 to kick off the classical and mannose-binding lectin pathways, and C1 esterase inhibitor regulates this process. When someone is missing this inhibition, it causes hereditary angioedema. As we saw previously, we have other mechanisms in place to protect us from overactive complement, so whatever complement is being activated is not clinically significant. Rather, hereditary angioedema happens because we are missing a different function of C1 inhibitor. Let's go to the whiteboard a moment. It so happens that C1 inhibitor also plays a role in inhibiting parts of the coagulation and kinin-generating pathways. When tissue is injured, phospholipids released from damaged cells cause local activation of contact system proteases, including Hagman factor, which is factor 12, and prekallikrein, and this kicks off the clotting process. Once activated to 12A and kallikrein, these proteins can help cleave a molecule called high molecular weight kininogen to form bradykinin. Bradykinin is a mediator of inflammation which causes smooth muscle contraction, vasodilation, and pain. And you may recall that angiotensin converting enzyme helps break down bradykinin. Keep this in your back pocket for a second. So it turns out that when you are missing C1 inhibitor, you get an unregulated activation of kallikrein, which we just saw will lead to high levels of bradykinin, which is the root cause of angioedema. The result is a ton of swelling with very little insult. So it makes sense that the hallmark of this pathology is edema, mainly of the dermis and subcutaneous tissue, and especially around the eyes, like this poor kid here, and also of the mucosa. Airway swelling can be fatal, and patients can even get swelling of the GI tract. The buzz phrase here is swelling without urticaria. Urticaria, or hives, are brought on by histamine. This drives home the point that this is not a histamine-related allergic reaction and has a different mechanism. Because this is a different process, epinephrine won't work. You need to basically give back what they don't have and treat with C1 inhibitor concentrate, which can be found in fresh frozen plasma. If in a passage someone comes in with a swollen face and they are treated with epi, but it doesn't work, think angioedema. A good screening test is to look for low C4 levels because the classical pathway is being triggered. And ACE inhibitors, which are used to treat high blood pressure and heart failure, are absolutely contraindicated in these patients. This makes sense because we just saw that angiotensin-converting enzyme helps break down bradykinin. If it's inhibited, there will be more bradykinin around. In fact, a side effect of ACE inhibitors is angioedema, which could happen even without the hereditary form because of raised bradykinin levels. And the famous ACE inhibitor cough is also thought to be mediated by bradykinin-induced bronchospasm. And that's the end of our lecture on innate immunity. Here's a brief summary of what we've discussed so far. Macrophages are the sentinel cells of the innate immune system, and cells of the innate system are activated by PAMPs binding toll-like receptors. Macrophages recruit neutrophils and activate natural killer cells by releasing cytokines when fighting infection. Neutrophils exit the blood and are destructive cells that kill by reactive oxygen species and by releasing contents of granules. The innate system is not great at fighting intracellular viruses, but natural killer cells help with this. Mast cells and eosinophils help fight parasites and mediate allergic reaction. Complement can directly kill pathogens using the MAC and also aid phagocytosis. And last but not least, dendritic cells are antigen-presenting cells that can travel to recruit adaptive immune cells, thereby boosting the immune response. Thanks for watching, and check out our other videos covering boards immunology. In the next video, we will see what activated T cells can do to kick the immune system into high gear. If you like this video, share with your classmates and friends, give it a big thumbs up, and hit the pathognomonic icon to subscribe to the channel. And we'll be coming out with more videos on other high-yield boards topics, so ring the bell if you'd like notifications. And as always, please leave your comments below and tell us what we're doing well and where we can improve. Thanks for watching, and I'll see you next time.